Hello, everyone. Welcome to today's live broadcast. Time for a change? Changing solvents, acids, and reagents in analysis methods. I'm Bob Aliberta, Special Projects Director, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by Specs. Now I'd like to share a quick statement from our sponsor. Specs is a market leader of high-quality, innovative, inorganic, and organic certified reference materials and PT. They strive to exceed customer expectations by forming collaborative relationships and maintaining highly skilled employees in a positive, creative working environment. Their products are used in laboratories worldwide, conforming to international environmental and safety standards. They operate with integrity in all relationships with customers, employees, suppliers, the environment, and the wider community. All right, just a few quick important announcements before we begin today's presentation. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit your questions by typing them in the Q&A box, which can be found at the bottom of the video player. You can also enlarge the slide window by clicking on the small icon in the bottom right corner of the media player. The slides will advance automatically during the event, and if you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the top right of your presentation window. All right, I'd now like to introduce today's speaker. We are pleased to be joined today by Patricia Atkins. Patricia Atkins is a global product manager at Specs, NSI, HPS Chiron, where she has been a scientist for the past 15 years. She's a graduate of Rutgers University and was a laboratory supervisor for Ciba Specialty Chemicals. Patricia managed and conducted research in air pollution at Rutgers University before moving to Specs. She has been involved with many industry-focused advisory organizations and is a frequent presenter at conferences. Patricia is also a published author, with her work appearing in journals and trade publications, including Spectroscopy, LCGC, and Cannabis Science and Technology, where she is a columnist for analytical issues in cannabis testing. Thank you so much for joining us today, Patricia. Please take it away.
Hi, welcome to today's presentation. Time for a change, changing chemical components in analytical methods. My name is Patricia Atkins, and I am the Global Product Manager for Specialty Chemicals, including Specs, NSI, HPS, and Chiron. So why would you ever change your chemical components? Why would you change solvents and buffers and reagents? Is there really a reason? Well, of course there is. There could be an issue of efficiency. Maybe it's been found that a particular solvent or a particular gas or a particular reagent is much more efficient than the one that you've been traditionally using. Maybe there's been a dramatic cost increase. Acetonitrile a few years ago was very, very expensive due to a shortage of acetonitrile. Helium, the cost of helium has gone up as there's shortages of helium. So maybe there's a cost issue. Maybe you've had a process improvement or some sort of technical improvement. You bought a new instrument or a new extraction unit or a new digestion unit, and it's much more efficient, so maybe you can now change to a different type of chemical component. Maybe there are real-world consequences to changing to different components. It could be an issue of health and safety. It could be an issue of waste or potential contamination or environmental pollution. Or you might just be mandated to do it because of some regulation or law that's been enacted. And these three tend to be very interconnected. Usually there is the component of health, safety, the environment, waste, and a legal ramification for not changing. In the 1990s, a movement started for what is now called green chemistry. This was the idea put forth by the EPA and also OSHA and the government to try to encourage chemistry that would be beneficial for the earth, that would cause less pollution and contamination, that would be good for human health, that would have less carcinogens and other health exposures to some dangerous chemicals, and also would encourage less waste and more reuse. So in the 1990s, we started to see legislation that was being enacted in order to examine these chemicals and start to put plans in place for the phasing out of these dangerous chemicals. Out of the movement towards green chemistry, the 12 principles of green chemistry were born. The first is prevention of waste, trying to control the process so that less waste is created. Atom economy, trying to design reactions and processes which use the entirety of the reactants so that there is no leftover. Reducing chemical hazard synthesis, so just reducing the different chemicals that are hazardous to begin with, or trying to find products that are alternative and less hazardous. Design safer chemicals that are safer to produce and safer to use. Use safer solvents and auxiliaries or other compounds. So trying to find materials that can be used in place of dangerous solvents and other chemical compounds. Energy efficiency. If a reaction can be done at room temperature instead of at heat where energy is applied, then that method or that procedure should be followed. Likewise, you should be using renewable feedstocks. So whenever possible, to use renewable chemicals and renewable feedstocks, like hydrogen generation instead of helium use, or nitrogen generation. Reduce derivatives, stopping protective blocking agents or functional groups that will stop a chemical from degrading or produce excess waste. Catalysts, using catalysts which can then be returned to its original form and used again instead of stoichiometric reactions which consume the products. Integrating degradation by design, so planning for the obsolescence of a compound. Modern day pesticides have a degradation planned into them. There is a obsolescence planned into how some chemicals will break down in the environment over a period of time. Real-time pollution analysis, building into the process a system where you can actually monitor the potential for pollution or the pollution being generated by the process or the chemical that's being created. And safer chemistry for accident prevention, making sure that all of the processes are safer for human health and basically stopping a problem before it starts or stopping an accident before it happens. We are going to focus right now, though, on the solvents, about what are safer choices for solvents and how you can choose that safer solvent without damaging your process or without not being able to do the process that you need to accomplish. Move to safer solvents saw the classification or the moving of different solvents into classifications where they were either potentially very harmful, they were potentially very useful and had low impact on the environment and human health, or there was a middle ground where there still were some concerns, but there was potential to use this middle ground, these yellow solvents. And these are not a complete list. This is just a small list of potentially good or usable and harmful solvents that are very common to chemistry. We have on the harmful list the players that we would expect to see there: benzene, carbon tetrachloride, chloroform, the ethers, dichloromethane, hexane, pentane, things like that. So these are chemicals that are in the laboratory and that we tend to be very careful with because we understand them to be very dangerous or potentially very dangerous for long-term health. Then you have things like we use all the time: acetonitrile, MTBE, DMSO, tetrahydrofuran, these have some inherent danger to them, some inherent health risk, inherent environmental risks, but they are deemed possibly usable or a slightly safer alternative than to the harmful chemicals. Then you have the good list. These are the ones that have the lowest impact to human health and the environment as far as routine use in laboratories and in industry. Things like acetone and ethanol and methanol, things that we're very, very familiar with in our laboratories. So part of what EPA does with TSCA is to review different chemical materials, different chemical substances, and make a determination whether or not there should be some sort of plan to decommission or reduce or restrict the use of those chemicals to the greater public and to industry. So there have been a lot of potential targets for some sort of a remediation effort or restriction effort by the government. Some of which we are familiar with, things like the refrigerants that have been limited and banned, some phthalates that have been limited and banned in certain certain children's toys and other things like that, that have all come through work that has done with the Consumer Product Safety Commission or EPA or TSCA or sometimes a concerted effort between all of them. One of the more recent efforts started in 2022 and was just announced in spring of 2023, and it is a limitation and ban on methylene chloride. Now, they're looking for a limitation or a ban of use of methylene chloride for many industrial uses, and often when they ban a particular chemical or limit a particular chemical, they do it for mass production or mass industry and manufacturing, but laboratories have often enjoyed a certain amount of exemption to some of these restrictions due to the nature of the work that they do. But in this case, this particular restriction is calling for concentrations of at or under 2 ppm over an 8-hour period, and in a 15-minute exposure, you have to have a likely 15-minute exposure of approximately 16 parts per million or less. So they are now putting restrictions on how much methylene chloride a laboratory personnel could be exposed to, what the air concentration would be for methylene chloride in a particular laboratory. And then depending on the laboratory and how much methylene chloride is used and how it's used, this might be very difficult to reach these limits. So then they're faced with a choice. Do you replace methylene chloride altogether? Do you change your solvent? Do you reduce its use, either by changing your processes so you use less of the methylene chloride, or you use it at a smaller scale? And then finally, can you reduce it by creating some sort of hybrid where you use less and you substitute some safer solvent or safer chemical or buffer in the process to replace that material, so or that methylene chloride, so then you are having less exposure, airborne exposure to methylene chloride in the laboratories. Now laboratories are left with a puzzle, a conundrum. They're being forced to replace or reduce methylene chloride, which has probably been written into their methods for decades. And they're being asked to find a suitable alternative or to change their processes. So what can they do? Do they find a new process? Do they find a new solvent? Or maybe it's a buffer, or maybe they need to change their reactions and their reagents. Maybe they need a new mixture of different things. So it becomes a research project to try to figure out, how do you replace something that has been integral to a process for a very long period of time? Well, you have to get back to the basics. What are your starting points? Starting points are, what are the properties that are important about methylene chloride that you have to then duplicate or try to cover in a new solvent or a new mixture? How does this function? Will it function the same way for the same job that it's doing? And is it fit for purpose? You can't just, like I said, take an extraction solvent like methylene chloride and replace it with water. You cannot use certain solvents if you're doing a GC analysis, just like you can't use certain solvents if you're doing LC or LCMS analysis. So it has to be fit for the purpose. But this replacement can be a lot of things. We've bounced around a lot of terms, reagents and substance and chemical and compound, and sometimes we tend to use them very freely, forgetting that there are differences and subtle differences. So just to make sure we're all speaking the same language, let's go back to the beginning for one step. This might be a little too basic, but let's just start from the beginning. Atoms and elements, we're all familiar with what atoms and elements are. And when you put them together, you get molecules. You put the molecules together, two or more atoms or elements, and you chemically bond them, and you get compounds and complexes. And those bonds are created or broken through reactions and usually have a change in energy. So you put two molecules together, and there's a chemical reaction, and they heat up, or it cooled down and they're cold. On the other side, you have mixtures. You take two or more compounds that are not chemically bonded, and each of these compounds still retains their properties. So if I take sucrose and I take a solution of iced tea and I mix them together for sweet tea, they retain the property. The sugar is the sugar and the tea is the tea. And if I dried out the iced tea and I evaporated off all of the water in the iced tea, I would be left with tea powder and sugar powder that I should then be able to separate. And there's no to little energy when these are formed. There's no change in energy. So when I mix my sugar in my iced tea, it doesn't heat up. And if I mix my sugar into hot tea, it doesn't really cool it down. The mixing might cool it down, but the sugar itself is not going to cool it down. And they are separable in some way, either by filtration or chromatography or distillation, purification, electrolysis, heat, or centrifuging. So there is a possibility for separation. Now, what we're going to look at next are the different types of mixtures. Three basic types of mixtures: a suspension, a colloid, and a solution. The suspension are large particle substances in a media that is prone to sedimentation. And this is a very heterogeneous mixture. This is a mixture of sand and water or silt in water. You have a colloid. This is a homogeneous mixture of very small particles dispersed through a medium or another substance. And there is a suspension of the particles within the matrix of the medium that they are suspended in, but it's suspended in a homogeneous fashion. Then you have a solution. This is a homogeneous mixture of substances in a medium where the particles of the substances cannot be distinguished by the naked eye. So if I take my iced tea and I mix my sugar up and I don't create a hyper or supersaturated solution, then I am not going to see any sugar crystals on the bottom. I am only going to see tea in my glass. Here's a little table of some of the distinguishing characteristics of a solution, a colloid, and a suspension. As I said, a solution and a colloid are homogeneous and they have small particle sizes. Suspension, heterogeneous, large particle sizes. For the suspension, there's a possibility of settling out. The colloid, you might not really get true settling out. You can get division into phases. You can get some stratification. And with the suspension, you can actually separate it by filtration. So think of basically muddy water through a very fine micron filter to remove all of the dirt and mud particles. And then the suspension, you're going to have light scattering. A colloid, you can, depending on what the medium, might have light scattering. It might be opaque, or you might have only minimal light scattering. And then a solution, you're not going to have any light scattering. Now let's take a look at some of those examples. We have a gas, Dissolved, that's air. So you think about air. Air is a good example of a gas-gas solution. For a gas liquid colloid, you could say like that's hairspray or clouds. That is when you have your gas being dissolved in with a liquid, and then you have a cloud formation. If you also have a suspension, that's kind of like mist in air. For solids, you can have smoke, which is a solid that is suspended in a gas. Dust, smoke, that's an aerosol. For a liquid, for a colloid, you can have an emulsion like mayonnaise or milk. And if you whip it, you have a foam. That's gas being introduced into a liquid like whipped cream or soap lather. For your solid into a liquid for a solution, there's my sweet tea example where I've added sugar to my sweet tea. And even blood is a colloid. It is solid dissolved into a liquid. This also can be applied to paint and ink. When it comes to solids and colloids, think of styrofoam. Well, that's appetizing. Well, no, think of cake and bread. Cake and bread is definitely more appetizing. You have the gas dissolved into a solid. It puffs the cake up, and then you get your beautiful cake or bread. For a solid into a solid solution, you have your alloys. Your liquid into a solid, you have an amalgam like on your teeth. So there are a lot of different examples. Gemstones are even an example of a solid into a solid. Those are a colloid of a solid into a solid. So there are a lot of really interesting examples of these types of mixtures. So as we're on a hunt to replace our chemical substances, in particular our solvents, let's go through some of the terminology, because some of the other chemical substances, we tend to use the terminology a little loosely. And I know for myself, sometimes I misuse some of the terminology. And just to be clear, we said we're starting from the beginning and we're going to clarify ourselves. A reagent is added to a reactant to create a chemical reaction. So it is added to the system to create the chemical reaction. Then you have the indicator. This is a reagent that is added to create a color change, something like phenolphthalein or bromocresol blue, elements of wet chemistry or classical chemistry. So you titrate your buffer or your material, your acid or your solution, you create that color change, and you then get a signal that the reaction has gone to its completion. Then you have your catalysts. Your catalysts drive or initiate a reaction without being consumed by it. Solvent are actual compounds or solutions that dissolve a solute into another solution. So you can have a solvent that is a solution. If you have a solvent that is a certain percentage, let's say of water, or a certain percentage like a blend of solvents, that's actually a solution. So you can have a solution that is a solvent and a solvent that is a solution. So then you also have then buffers. Buffers are solutions which do not change in pH. And then you have acids and bases, and they kind of play in all the realms. So there are acids that act as reagents. There are acids that can be added and used in a fashion of a solvent. So there are multiple applications for acids and bases. So these are solutions of compounds that accept or donate your protons. In your standard solution, as we said, it is a solvent plus a solute. It results in a homogeneous mixture. And light beams can't scatter it, as we said, and it cannot be separated by filtration. But it is stable and there is no precipitation. And it is one phase. It is miscible and or soluble depending on what your solute and solvent are. When we talk about the types of solutions, there are three scenarios. In the first scenario, you have a large proportion of solvent and a small proportion of a solute. This is a hypotonic solution, less solute than solvent. Then you have the isotonic solution. where your solvent and your solute are equivalent. They're in equal proportions. And then finally, your hypertonic solution, where you have more solute than solvent. And this is more proportioned to the larger proportion of the solute rather than the normal way we think of solutions where we have a large solvent volume. Another two terms that we confuse a lot are miscibility and solubility. Miscibility means they mix it in all proportions. It doesn't matter if one is 70, the other is 30, or if they're 50-50 in all proportions. And we are often referring to liquids when we're talking about miscibility. This is a miscibility chart for common solvents. So you can see that if you have acetone in all the solvents that are listed, it is miscible in all the solvents. But something like water is not miscible with a lot of different solvents. It's not miscible with dichloromethane or the DCM we've been talking about. It's not miscible with hexanes or heptanes. So that is immiscibility. So you have miscible where it mixes at all proportions and immiscibility where it does not mix at all proportions. Then you have solubility. This is limited proportions. So you might have some solubility of one particular solvent into another, but not at all proportions. This is solubility. Predominantly, though, we talk about solids for solubility. When you also talk about solvent solubility, you want to know what type of solution. How saturated is this solution? An unsaturated solution means more solute can be added. It's got a low solute concentration. A saturated solution means you've reached the saturation point and no more of your solute will dissolve in your solution without precipitating. And then finally, you have a supersaturated or a hypersaturated solution. And this is where you have precipitates forming, crystals falling out, the settling of undissolved solute. Often the solubility of any particular material has a limit, and it also has a behavior due to a temperature. So sometimes by heating a particular solvent and introducing your solute, you can actually increase the solubility. And in some cases, there is a sweet spot for solubility of a particular material. So there are solubility curves for different solvents and different materials, and they're often based on temperature. Other factors which can affect solubility are surface area and the boundary layer thickness between the solute and the solvent, how well it's mixed, how long it's mixed for. So these can all be calculated to give you your solvent solubility. So let's now try to sort out some solvents. The first thing we often do is try to figure out, is what we're doing fit for our purpose? We have to look at the chemistry, the workflow, what technology we're going to be employing, and then the methodology we're going to be employing. First, for chemistry, what are the properties of what we're trying to replace? What are the properties of the targets that we are trying to extract or analyze? How much level of impurities and what impurities can we stand with a replacement? What impurities exist in the original solvent or reagent? What's the target and what is our matrix? Do we have to consider the target and the matrix when we choose a different solvent or a different reagent? Are we going to be using this new compound or this new substance for part of our processing? Or are we going to be using it for analysis? Are we going to be doing extraction or digestion? Are we going to be doing chromatography, spectroscopies, spectrometry, spectrophotometry? And what method are we going to do? Are we going to do FSC? Or are we going to do microwave? Are we going to do LC or GC or some other type of chromatography? For today, we're really just going to focus on the chromatography and the mass spec and the LC and the GC. Let's look at the chemistry and give a check for chemistry. Are we going to be really needing to dive into the type and the class? Alkanes, alcohols, polar, ketones, nonpolar. So what type and class are we trying to replace and what are we trying to replace it with? What are the properties of those particular solvents? What's the boiling point, the molecular weight, the polarity index, UV cutoff, things that are going to be important, especially things like elution strength and solubility and miscibility. Are the properties that we are trying to recapture in a new solvent covered by that new solvent? And then what are the specifications? What are the grade, the purities, the impurities of the material that we're going to buy or the solvent we're going to buy? And we have to consider this chemistry for both the targets that we are trying to analyze and the solvent we are replacing and the solvent we are replacing it with. So let's focus first backwards on the specifications: grade, purity, impurities. There can be a lot of choices when it comes to grade of solvents. Is it a general purpose that we're trying to replace? Do you want a general purpose solvent, an ACS grade, for instance? That means it exceeds or meets the ACS specifications. Are we doing a water-sensitive reaction? Then we're going to want an anhydrous solvent. That usually means very low water levels. If you are doing LCMS for very, very delicate LCMS analysis, then you might want to consider LCMS solvent grades or pesticide residue grades for GC and GCMS. So each type of solvent or grade of solvent will have its different applied use or suggested use and its analytical benchmarks or its analytical properties that would be helpful. So if you're going to be using it for, let's say, UV vis, you want like a spectrophotometric grade, so you can use it with UV vis applications. Well, how pure is pure? How many nines? What % purity should you be using? Well, that will depend a lot on how much impurity your particular process or your application can stand. So if you say, oh, well, I have 99.9% pure, that's 3 nines, but that means there are 1,000 ppm of impurities in that material. Is that acceptable? It might be. It might not be. So you can see that if you go down to 4 nines, you only have 100 ppm of impurity. And if you're doing PPB work, you might want to be looking at 99.99 or even 99.997, which is 4.5 nines. Because the lower you go with the impurities, then the better off you are seeing your very small trace analytical targets. So what level impurities will not fit your purpose? I like to show the level of what a trace concentration looks like. We all understand ppm and ppb, but when you compare it in real-world terms, it's actually a little bit startling. In time, 1 ppm is 1 second in 11.6 days. 1 ppb is 1 second in 32 years. For money, 1 ppm is 1 penny in $10,000, while a ppb is 1 penny in $10 million. So if we're talking about levels of impurities, which level of impurity can you stand? Can you stand the 1 ppm or the 1 ppb? The 100 ppm or the 1,000 ppm? Which level of impurities can your analysis stand? There is also the principle of Horwitz equation or Horwitz trumpet, where the percent RSD is proportional to your target concentration. So if you have a large target concentration, you can achieve a very small relative standard deviation. But as you move to ppm and ppb, you start to get this dramatic increase or rise in your percent RSD. So you want to keep the impurities as low as possible when you're doing the PPB analysis because you have a hard enough time with your percent RSD being very large. I decided to include this unit conversion chart. This is actually something that lives on my desk or lives in my work area when I'm using it because, in all honesty, switching back and forth between units can be sometimes second nature for some of us, but for most of us, we like to double check that we're changing our units. And when we get down to the ppb and ppm and concentrations and weight and weight volume, I like to have a cheat sheet next to me. So I gave you our specs unit conversion cheat sheet, and it is downloadable from our website. So now let's take a look at the class and type. This will help you make some decisions when you are replacing your solvents. One way that solvents are divided are by whether or not they're hydrocarbon, whether they're oxygenated, or whether they're halogenated. So the hydrocarbons tend to be the aromatic and the aliphatic hydrocarbons, and they tend to be the non-polar solvents that we use. Things like our hexane and our cyclohexane. Then we have the oxygenated solvents, our alcohols, our ketones, aldehydes, and our ethers. Those are polar solvents. And then finally we have our halogenated solvents, our chlorides, our bromines, and our fluorides. These are all polar solvents. Now the polar solvents can be further classified into protic, amphiprotic, or aprotic. So the protic are obviously the ones that have the OH groups or have available oxygen. The aprotic are the ones that do not have that ability. Another way that we look at solvents sometimes is, are they applicable to GC or HPLC? If you're doing reversed phase HPLC, then you really want the polar solvents. You want the high polarity index. So you want things that are about 4 and above, and which of course water is at 10 is basically the ultimate polar solvent. For GC polarity, you don't want polar solvents. You want nonpolar solvents, and this is also in the range of normal phase chromatography. With GC, you have other considerations as well, though, like molecular weight and boiling point. This is where you can see polarity matter for your instrumentation. If you have nonpolar targets, you have environmental targets that are very nonpolar, then you are probably also using some only slightly polar or nonpolar solvents, and that means you'll be doing GCMS for the most part. You also could be, in some cases, doing normal phase HPLC as well. If you have very polar solvents that you're using and very polar compounds, then you are on the other end of the scale. You're probably doing LCMS with electrospray. Where you look at DCM, DCM kind of lives in the area within GC and normal phase liquid chromatography. So it kind of lives between that nonpolar and slightly polar area. There is something called the Snyder triangle for chromatography that shows that if you put at the base a proton donor, a proton acceptor, and the dipole interaction, and you plot the different groupings of solvents, you can see where they lie on this plot of proton acceptor, proton donor, or dipole interaction. When it comes to DCM, that falls into number 5. That's where you have the dichloromethane, the dichloroethane, ethylene chloride, things like that. And there aren't a lot in that group. And you can see it's very far away from being the proton acceptor or the proton donor. The closest classifications are 6 and 7. These are things like ketones, esters, dioxin, nitriles, things like ACN, acetone. And you also have things like ethyl acetate. And then number 7, you have aromatic hydrocarbons and nitrogen compounds. So if we're looking at chromatographically, the most similar type of solvent that we have to DCM are in this groups 6 and 7. What's the elution power? If you're doing liquid chromatography, you would care on what's the elution strength or elution power of your particular solvent. The ability of the solvent or the mobile phase to pull an analyte away from the stationary phase. And this is very much dependent on polarity, the polarity of the mobile phase and polarity of the stationary phase. For the most part, things like alkanes and cyclohexane, they have a very low elution power, less than 0.1 allotropic value, and this means they are more in that world of normal phase HPLC. As you move down the chart, you can see there's our dichloromethane, our DCM, with a value of a 0.4, and it puts it basically in that normal phase range as well for HPLC. As you climb more, then you see more of your reversed phase chromatography, reverse phase HPLC solvents and mobile phases, your ethyl acetates, your acetonitrile, your isopropanol, and etc. Of course, water is the highest at over 1. Now, if you look at some of the ones that surround the tetrahydrofuran and the toluene and the ethyl acetate and the acetone, they surround that dichloromethane. So these, when it comes to the strength, the elution power, are falling in the same range. And the ethyl acetate and the acetone were part of the choices in the previous slide where we saw chromatographically the groupings that were similar to the dichloromethane. If you're doing UV, like HPLC, UV vis, then you actually do care about, is there any active UV cutoff in your solvent? So for methylene chloride, it's 233. So it will be visible in your diode array or your UV vis. Something like a propanol has a lower UV cutoff. Acetonitrile is always a good choice because it has a UV cutoff of 190, so most of the wavelengths that are monitored are above 190. Another way to look at polarity, and it also is related to that elution strength that we were looking at before. So the highest polarity is water at 10.2, and the lowest polarity are those alkanes at 0.1. Now, when you mix two solvents of different polarities, you actually get a different polarity for the mixture itself. So if we take our friend dichloromethane that we're trying to phase out and we pair it with its neighbor that we saw in the triangle before, ethyl acetate, we say, okay, let's reduce our DCM to 20% and we will put in 80% ethyl acetate. So you perform the calculation, you take the polarity index by the percentage, and you get a value. You add those two values together, and now you get the new polarity index for the mixture itself. And in this case, when you have an 80-20 ethyl acetate and DCM added together, you have a new polarity index of 4.1. Whereas if you were 100% of dichloromethane, you would be at 3.1. So then a decision can be made through experimental testing whether or not this would be a good choice for partially removing or reducing the amount of dichloromethane. When choosing HPLC solvents, you're going to need to be aware of the UV cutoff and the polarity index more than many other factors, especially if you're doing UV vis. As we said, you're going to want it to basically be invisible when you're looking at your target compounds. So you're not going to want a UV cutoff in the range of where you're looking for compounds. So you're not going to want things in the 254 or the 255 range. You're going to probably not want things in the 230 range. And that means that methylene chloride, for the most part, is going to be problematic. You're also going to want high polarities. Acetonitrile with its nearly 6 is a very good polarity for reverse phase HPLC. Water, of course, is one of the best reverse phase HPLC solvents and mobile phases. For GC solvents, you have a different set of priorities. You're going to care more about the boiling point and the molecular weight. You're going to want low molecular weight solvents, things that are going to be very volatile and have very low boiling points so that they evaporate or they volatilize very quickly in the source and allow for the target analytes to move through the mobile phase and the solid phase of the gas chromatography system. So when it comes to actual molecular weight and boiling point, this makes methylene chloride a really good solvent for GC because of its volatility. So that becomes important when you're looking for a replacement to methylene chloride, that you look for something that has a very similar properties. So ethyl acetate that we saw before is a very good choice as far as molecular weight, because it's a very similar molecular weight, and it has a somewhat higher boiling point than methylene chloride, but it's still not one of the highest boiling points that could be possible for a GC solvent. It is this low boiling point and this high volatility that actually becomes a safety concern when dealing with some of these solvents. You can see dichloromethane, or DCM, has a boiling point of 40 degrees C, so it could volatilize very quickly in a hot room, or over time. It has very high evaporation rates. So if you have an analyst sitting near a waste container or a collection site, there could be significant exposure to vapors from solvents. So our other company, Cole Palmer Essentials, actually sells a product called Vape Lock, which allows you to trap the vapors in the waste containers so they are not contaminating in the laboratory. There has been a lot of research done on replacing potentially hazardous solvents with safer solvents. In particular, since the last year or so, there has been research into replacing dichloromethane with other alternative solvents. Most of them are aprotic, and they are also, for the most part, polar solvents with a variety of different boiling points. So I've given you a table of some of the most sourced alternative solvents, and some of the notes. Some of these were tested for extraction. Some of these were tested for thin layer chromatography. There also were some mixtures of different proportional mixtures of solvents using some of the ones in the gray box. And if you want to read any of these papers about dichloromethane replacement or safer solvents, I've included the citations there that you can look some of these papers up and look into some of these alternative solvents. I want to thank you today for listening to our presentation. And just to close, I want to remind everyone that Specs offers a full line of solvent CRMs, whether it's the hazardous solvents or some of the safer solvents. We offer certified reference materials for all of the different solvents and hundreds, if not thousands, of other chemical compounds. To our certified reference materials, Specs now offers solvents. So you can choose some alternative solvents, or if you still have methods that need methylene chloride, we will be happy to provide you with quality solvents. Again, I hope you've enjoyed our presentation and found it valuable. You can find more information about our certified reference material products, our spec solvents, and our Cole Palmer line of solvents on our website. So thank you again, and I think we might have some time for some questions.
If we're ready to go, we will jump into the Q&A portion of the event. Just before we get started, I'd like to remind the audience how to submit questions. So you can submit your questions by typing them in the Q&A box, which can be found directly below the video player. And these questions will be answered by Patty during our Q&A session. So jumping right in, Patricia, does the grade of solvents matter, or is it just marketing used by manufacturers?
Well, the grade of solvents can matter. If you are really having a trace analysis, then yes, the grade of solvent is going to matter. You're going to want to make sure that the specifications for the solvent that you're using matches the specifications for the analysis. So yeah, some of it is marketing. Some they're ultra purists, or they're ultra pure, or they're purissima. So all the manufacturers have their different ways of describing their solvents, but at their heart, there are some differences in the grades of solvents.
It's good to know. A little marketing spin, but there is some truth to it. So next question here from the audience, is LCMS grade worth the extra expense?
Yeah, LCMS grade can be worth the extra expense, especially if you're doing trace analysis. I've personally used the HPLC grade and the LCMS grade. And when I was doing PPB work, I did find there was a much lower baseline with the LCMS solvents. So I did, in some applications, use LCMS solvents.
Excellent. Thank you for that info there. And follow up here, do laboratories that produce their own DI water have to purchase other grades of water?
Well, DI water is really great for a lot of general purpose applications. And there are some filtration companies that sell add-on systems to DI water to polish it for different applications. So if you have one of those systems and you're doing LC or LCMS, you can certainly make your water in-house from your DI water. But if you do not have one of those extra systems, then DI water is not usually good for some applications like chromatography. There tends to be a lot of phthalates in the lines for DI water. So it depends on your DI system and to what level it deionizes and what type of tubing and transport you have in your laboratory. DI is great for general purpose. For organics, it tends to be a little less helpful. For metals, DI water can be fantastic.
Fantastic. Thank you for that. And switching gears a little bit to solvents then, what's the best way to determine if a substitute solvent is as effective as the original solvent?
Well, you really do have to do your testing. So one of the ways you can prove whether a solvent is effective or not is to spike your potential samples with a standard, and then you can actually monitor the recovery efficiency of your extraction and your analytical efficiency of changing that solvent. So that's one of the surefire ways. But you are going to have to do a little bit of in-house work to see if the changes you're making, and you might be using different solvents for different things. You might be using one replacement solvent for your extraction and then another replacement for your actual analytical method.
Great answer there. Well said. And is it better to buy blended solvents or blend them in-house?
Well, you can do both. If you are going to be using large bulks of solvents and you're using them constantly and you have personal time to make them, you can blend them in-house. If you are going to be using them and for a few projects and then they're going to get stored, then you probably want to buy solvents that are stable. The other side of the coin is that once you've opened up a bottle of a mixture of solvents, then you've started the clock on it. So I guess it depends on how much you're going to use and how quickly you're going to use it. Some solvents also tend to pick up contamination very quickly once you've opened the bottle or once you've made up your mixture. So they both have value, and I think it really depends on how much you're going to go through and how quickly you're going to go through those solvents.
Excellent. So I think with that, we will wrap up. Thank you so much, Patricia, for your time and your expertise with the question and answer session. So, of course, I want to thank the audience for attending and for participating in today's event. Again, a reminder that this will be available on demand for replay. You'll receive an invite to the on-demand replay within 24 hours, and any audio issues that we may have experienced during the event will be corrected at that time. I'd also like to thank our sponsor, Specs, for making today's webcast possible. We'd also like to thank everyone. We'd also like to ask everyone in the audience to please participate in a brief survey. This survey will appear on your screen after today's presentation has ended. All right, we hope to see you all next time. Take care, everybody.